In this video, we'd like to go ahead and take a look at applying calculus to being able to find the charge on a capacitor that's being, while it's charging up, find the charge in the capacitor as a function of time. Like I said, it's going to use a little bit of calculus because of the way that the voltage on the capacitor is going to be changing as it charges up, making it more and more difficult to push charge to the plates. And so the rate at which the charge is changing will be changing. And it depends on how much charge is there. So you have the charge and the rate of change of charge influencing each other. So we're going to get a differential equation out. But before we dive into that, let's quickly review what the different initial conditions are and the final current conditions will be for this circuit as we're going from the capacitor being completely uncharged to being fully charged. So again, we recognize this sheet. I'm just going to very quickly run through the initial and final conditions so that we know kind of where we're coming from, where we're headed to. Let's go ahead and start with charge on the capacitor. We know that at time 0, the charge on the capacitor will be 0. We're starting with this capacitor uncharged, and time 0 is when we flip the switch and turn the circuit on. We know that eventually it will get to its maximum charge, which I'm just going to symbolize with a capital Q. And I'm going to put a little subscript Q max. All right, but that maximum charge, you say, well, can I describe that in terms of other variables that we have here? You say, well, yeah, we can, since we know using the formula for a capacitor that capacitance is the charge per delta V over the capacitor. We could rearrange this and we would get something like that Q max will be equal to the capacitance times that maximum voltage the capacitor gets. Because if I'm talking about Q max now, well, the maximum Q, our maximum voltage, right at the end, that's going to be equal to the voltage of the battery. So it's going to be equal to the capacitance times the EMF. That's what we call that script E, okay, the electromotive force. It's a terrible name for voltage, but it's the idealized voltage of the battery. So this is going to be equal to capacitance times that EMF. We remember that the way it's going to get there, that at first charge will flow very quickly onto the capacitor, but as that charge starts to build and build and build at this upper plate, right, and negatives at the lower plate, that makes it harder. I just did that backwards. These are the positive charges. These are the negative charges. Dang it. But I know that as charge builds, it gets harder and harder for more electrons to get pushed to this upper plate. And it gets harder and harder for to pull electrons off this lower plate. And so that charge, even though it's got a Q max here, right? Maybe the Q max is right here, right? That's capacitance times the EMF. You say it's going to be asymptotic. So that's like a horizontal asymptote, and my charge is going to approach it. Okay, never quite reach it, right? Okay, what about current in the circuit? Well, since you say, wait a minute, current, that's just dq dt, right? Okay, I really wish I'd made that a lowercase q to show that it was changing over time. But anyway, dq dt. And so you say, well, first, when I first flip the switch, there's no charge on the capacitor plate yet to kind of make it harder for charges to get there. There's not electrons there building up to repel yet. And so at the first instant, this capacitor just acts like a bare wire when I'm charging the circuit. So the only thing that's slowing the current down is going to be the resistance in the circuit. So I can just use Ohm's law. Delta V is IR. At the first instant, that delta V of the battery, there's no voltage change here because of the loop law. As I go around in a loop, if I go up voltage at the battery, if I go down voltage going through the resistor, right? Okay, because there's no voltage change here because the capacitor's not charged yet. So going up this, I go back down. The delta V for this is just going to be the EMF of the battery. So the current, if I rearrange this, my I would be delta V over R. But I know the delta V is actually just the EMF of the battery in that first instant, just for the first instant when I first close that switch. And so it's going to be the EMF over R. So that is that maximum current, is that current at the start. and that's going to be equal to the voltage of the battery over the resistance of the circuit. At time zero, at infinity, right? That's when this thing is fully charged. You say that that current is going to be stopped. When the capacitor is fully charged, no more charge can flow to the plates. There's no more flow in the circuit. It acts like a break in the wire that stops the flow. And so now there's no current flowing through that resistor at all. So at the end, I don't know what you want to call this, the I at infinity. The I of infinity. For your Doctor Who fans, you say that I at infinity, that would just be zero. There'd be no current. And so what this graph's going to look like, we're going to start off at this high value, right? Which we're going to say that's equal to the EMF over R. But we're going to head to infinity, or to zero, asymptotically as we head to infinite time. Okay, and it would take an infinite amount of time for the current to fully die. Okay, and that's it. Let's talk about the voltage over the capacitor. The voltage of the capacitor, that's, of course, if I were to hook up a voltmeter, perhaps from one side to the other side of the capacitor, right? This is going to measure my delta V for the capacitor. Once again, it's really the delta V that changed from one side to another. Oftentimes, the delta gets left off, like on AP exams. We'll talk about the voltage of the capacitor, VC. We know it's really a delta V from one side to the other. Anyway, that delta V of the capacitor, you say, at the start, the capacitor is not charged yet. And so there's no difference in V from one side to the other. So at the start, the delta V for the capacitor at the start, that would just be zero. However, at the end, it's fully charged, and it's now no more charge can flow to the plates of the capacitor. So nothing's flowing through the resistor. You say there's no charge flowing in the circuit at all. Well, that means, again, if I do the loop law, if there's no charge flowing through the resistor, there's no delta V over the resistor. So if I go up voltage from the battery, I better go back down that same voltage going through the capacitor. And so the delta V for the capacitor there is just going to be going down the voltage of the battery. Now, obviously, if I go one way, I'm going to go down voltage. If I go the other way, I'm going to be going up voltage from the negative plate to the positive plate. So kind of up to you how you want to represent this. I'm just going to say, for my own purposes, as I'm going around the circuit reading it this way, I would go up voltage in the battery. I'm going to go down voltage to the capacitor. So I'm going to mark it delta V for the capacitor at infinity. We're going to say that I'm going to write it as negative EMF of the battery. Now, a lot of people would go ahead and just call it the EMF of the battery, give you the magnitude of it, and that's okay if you want to plot it that way. But I'm going to plot it the other way to remind myself that as I go around in my loop, which I'm going to be doing the next calculation on the next page, I'm going to go up here and then down there. So it's going to start with a voltage of 0, and it's going to head to this final value, which is minus the EMF of the battery, minus the voltage of the battery. It'll approach it asymptotically. So it's going to be a curve like that. And now finally, let's do the delta V for the resistor. And again, this is going to be, if I were to say hook up a voltmeter, right, and measure my delta V here for the resistor. And you say, if I was going to do that at the start, in that first instant when you first flip the switch, again, there's no charge resisting flow on the capacitor yet. And so for the first instant, this acts like a bare wire, and the current is just going to whip around here through the resistor. If I go up voltage in the battery, I got to go down that voltage to the resistor because there's no V loss here. And so I'm just going to use Ohm's law for that resistor. Delta V is IR. And so you say, well, gosh, I'm going to go, you say delta V is IR, but you say the full current through, if you want to do it this way, is just going to be, we figured out at the start that was just E over R. So if I had delta V as IR, delta V is E over R times R. That's just going down by E, right? By the EMF, I mean. And you say that makes sense. You say at the start, I go up the voltage of the battery. I don't have a voltage drop here. I got to go down that EMF going through this. So again, depending on how you're reading the circuit, going this way, we're going to be going down potential. Going this way, we go up potential. I'm going to read the circuit clockwise when I do it later. So I'm going to mark this as saying at the start, my delta V of the resistor at the start, we're going to say that that's equal to minus the EMF of the battery. Again, a lot of times people just talk about it with the magnitude, just call it the EMF of the battery. But for my own purposes, I'm just mark it as negative. So starting here at 0, our final value, we're starting here with our initial value, I should say, of minus the EMF of the battery. And what's going to happen to this voltage? Well, as the capacitor builds up charge, the current flowing will die down, right? Our current is going to get less and less and less and less. And at the end, there's going to be no current flowing through here. And if there's no current flowing through, I is 0, then the delta V for the resistor is going to be 0. So at the end, there's no charge flowing. There must not be a change in potential. So there's a delta V, there'll be an E field pushing the charges through. There's nothing pushing the charge through the resistor anymore. So at the end, the delta V for the resistor is going to be 0. So this is going to be exponential decay graph as we're decaying down, approaching 0, closer, 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 closer. It takes an infinite amount of time to get there. So it's asymptotic to 0. And so that's the graphs. And you say, this is the situation we're going to be looking at. And you say, we're going to go ahead and whatever equations I come up with for these guys, my equations had better have these as my initial values, and I'll end up with these as my final values. And my graphs should, of course, be this shape. So let's go ahead and take a look at the actual calculation now, and how we're going to derive a formula to find these values, not just at the start and not just at infinite time, but to be able to find equations to find these at any point in time. Okay, so here's our circuit again with our battery with this EMF, a capacitance, and a resistance. Again, we could be having, in reality, this resistance could be split up between the wires. Maybe there's a big light bulb here or something that has a big resistance. And the resistance that's built into the battery, we can lump all those resistances into just one equivalent total resistance for the circuit. And again, I could have multiple capacitors and stuff, and this is just the equivalent capacitance for the whole circuit. But looking at this, we can get that feel for how this is going to work, and then we can start to apply it to more complicated circuits. But starting at this, you say, we're going to go ahead, and the way that we solve this problem, our starting point, the way we're going to get that differential equation out that relates V and the rate of, charge and the rate at which charge is flowing there, we're going to use Kirchhoff's loop law. We're going to say that delta V for a loop had better be 0. V is a value of a position, right? It's a value at a location. And so if I go around and end up back at that same location, my delta V had better be 0. And so I'm going to go ahead. I'm going to choose my path through this circuit. I'm going to choose to start at the low V side of the battery here, and I'm going to trace through the circuit going around clockwise here. Okay, ending up back where I started. Okay, is the path I'm choosing to follow. So let's do this. Let's run through. I'm going to add up all my delta V's going in the loop, and they should add up to 0. So running through, the first one we're going to do, going through the battery, we're going to go from the low V to the high V. We're going to go up the EMF of the battery. Okay, now I'm going to go through the capacitor. Now, at the start, you're right, the capacitor is uncharged. At the end, it's going to be fully charged. We want to find it at any point in time. So you say, hey, what's the delta V for a capacitor again? You say, I'm going to use the capacitance formula. This is the way I like to write it, as the Q per delta V. Charge on the plates. I'm writing it as a lowercase q to remind myself that it's a variable that can be changing over time. Over the delta V for the capacitor, which again will be changing over time. I'm going to rearrange this to find the delta V, and you say, well, this is going to give me delta V for the capacitor would be Q over C. All right, so this is going to go in for the delta V. I'm going to be going down potential though. I'm going from the high V side of the capacitor to the low V side of the capacitor, right? Remember, electrons are going to get pulled off this plate, drawn to this high potential section. So this will start losing electrons, become positive. Okay, electrons being pushed to this side of the plate, become negative. So I'm going down potential. So I'm going to go down Q over C. Okay. Now I'm continuing on. Here the current is flowing, right? Again, we say the current I know is going to flow from the high V side of the battery, trying to get around to low V side. I'm actually tracing this path in the same direction that the current is flowing. And the reason why I mention this is because we remember that the current, as we go through a resistor, we're going to drop voltage. We're going to go down delta V, right? My charge, if I'm thinking about my hypothetical positive charges flowing this way, as a hypothetical positive goes through, dumps off energy, it's got less energy per charge on the other side. If I do the math backwards with a negative charge, actually what's really happening is electrons flowing this way. Again, this is the side where the electrons haven't lost the energy yet. Here they have more, but I'm talking about energy per charge potential. You end up going up potential going to here. If you want me to talk about that later, I can talk about that. But this is definitely the high V side. This is the low V side of the resistor. So I'm going down voltage. How much voltage do I go down? Well, if I use Ohm's law, I say delta V is IR for a resistor. And so I just take the current times the resistance. And so you say, so I'm going to go down IR. Okay. And then that had better add up to be 0. You say, all right, when I look at this equation, you say that's a constant. Idealized batteries, the voltage is a constant for the circuit. Capacitance, that's a constant. It's built on just the shape of the capacitor and what's the dielectric in between, those things that aren't changing while the current flows. Again, ignoring effects of heating. And then you say, so the Q, though, the charge, that's a variable. Come over here, you say I, though, the current to the capacitor plates will be changing over time. When it gets fully charged, that current will be down to 0. It starts off being really big. So that's a variable. Resistance of the resistor, you say that's a constant. Remember, resistance of a wire is rho L over A. Rho is the resistivity for a material, which is constant, ignoring temperature effects. And then length and cross-sectional area we assume would be constant. And so you say, so that's constant. So it's really just Q and I have 2 variables here, right? Now, my goal, which I should have stated right away, is to find charge on the capacitor plates as a function of time. So I really want 2 variables to be Q and T, but I've got Q and I. Okay, fortunately, there's a nice relationship between charge and current, and time. And that, of course, is that current is dq dt. So if current is dq dt, you say, I'm just going to go ahead and substitute that in there. And so what my equation is going to look like now So now I have an equation with just 2 variables, Q and T, which is what I want. Q is a function of time. But I notice that I've got Q and its derivative. You say, this is a differential equation. And so that means we're going to have to do some tricks to solve it. What we're going to do is we're going to solve this by separation of variables. We're going to get all the Q's and DQ's on one side of the equation, all the T's and DT's. Okay, fine, the DT on the other side of the equation. And then we're going to integrate both sides. Now, to my mind, the hardest part of this problem for me personally is just the algebra part. All right, there's a little calculus involved, but the algebra part of rearranging and separating the variables. For whatever reason, I have had problems just doing the math to get the Q's and DQ's on one side, the T's and DT's on one other side. It freaks me out sometimes. I know it's just algebra, but still frustrating. So I have kind of a little procedure that I follow. It's probably not the simplest way of going through and getting there, but it helps me. I would challenge you to pause this video and rearrange this equation to get the Q's and DQ together on one side and the DT on the other so that you can integrate, right? So the Q, DQ, not in the denominator. You can't have this DT in the denominator. You've got both in the numerator, right? See if you can do that. Pause it and I'll wait. Okay, having tried that, let's see. I'm going to take you through the way I do it. Not the most efficient way, I'm sure, but it's what works for me. What I like to do is as my first step, I like to get the coefficient on Q to be positive 1. So I'm going to slide this to the other side, this term to the other side, and I'm going to do what I got to do to make the coefficient of my variable be plus 1. It's just what I do. So what I'm going to do is, again, I'm going to slide this to the other side of the equation. So I'm going to add over an r dq dt. So I just added r dq dt to both sides of the equation. This canceled out. So now I've got EMF minus q over c. Like I said, I like to get a coefficient of +1 on my variable, just for whatever reason. So to do that, I'm going to multiply through every term by -c. All right. So if I do that, multiplying by -c, this will become just positive q. Multiplied by -c, this will become minus capacitance times EMF. And multiply through by -c, I'll have negative RC dq dt. At this point, I'm going to say, hey, this chunk here, for the rest of this calculation, I'm going to treat this like one thing to move around. Okay. I'm almost done now. Treating this like one big variable or one big term. I'm now going to move the dt. I'm going to do something weird. Okay. Now this is sketchy mathematically. It's a little sketchy, but it works out. It's almost like I'm going to treat the dq and the dt like they're separate variables instead of one differential. I'm just going to move the dt to this side as if I'm multiplying by dt. I'm not really, but I'm going to treat it that way. Move the dt to this side. I'm going to move this chunk in parentheses, divide through by that chunk. So it'll be in the denominator over here. And then I'm going to move the negative RC over here. It's just the way I like to set it up. So is that too many algebra steps to do it once? Nah. Multiplying through both sides by dt is going to move the dt to this side. Dividing both sides by this thing in green, q minus c epsilon naught, means I'm going to have a 1 over q minus c. Did I say epsilon naught? That's not right. I'm sorry. This is the EMF. It's not epsilon. No. It's a script D. The dq I'm leaving there. This negative RC, I'm going to divide out both sides by negative RC. Okay, and this is it. I have now successfully separated my variables, right? I've got a side that's just got T's and DT's and a side that just has Q's and DQ's. This is the way I do it. Put those parens around that. And so now I am all set to integrate. So I'm going to go ahead and drop my integral sign. What is my issue here? Right, so I'm going to integrate. On this side, I'm integrating with respect to time. This side, integrating with respect to charge. Now, for this problem, I'm starting with the capacitor being completely uncharged, and then I'm going to go until it's fully charged. It's going to take, so I'm going to start with the charge on the capacitor being 0. My Q is 0. And I want to solve, now I'm not going to set this up to go to infinity. I'm trying to find an equation to find the charge at any point in time. So I'm just going to go to a variable charge Q on the plate. I'm not going to go from time 0, but I'm not going to go to infinity. I'm setting up the integral to find Q at any t. So I want this to go to a variable t. All right, so that's my bounds for my integrals. All right. Again, I'm going to run through this derivation. Recognize that on the AP exam, you may very well have a problem where you're looking at a situation where we're not going from 0 charge. Maybe it was already partway charged, and then that's when we start the clock. You know what I mean? So I might be starting at like a different charge than 0. Might be an interesting problem to take a look at. So, but we're doing here. So this case that we're doing here, it's like kind of the introductory case, and we can have some little changes to it. We'll come back and we'll take a look at what happens when we're discharging also. We'll start with a Q and then go to 0 or whatever. But anyway, that's for later. Okay, so let's move to do this calculus now. Okay. So go ahead and do in the calculus, you say, hey, this left side, that is not a bad integral to take. These are all constants. So it's just the integral of a constant times dt. So you say I just bump my variable up one level. So this is just going to be minus 1 over RC times t, evaluated from 0 to t. All right. And then that's right. And that's this side. And you say, hey, I can do that integral. You say, put in my bounds. And you say it's just going to be a minus t over RC. Okay, that's what's going to be on that side. On the other side, on the right side of the equation, you say that integral is a little bit trickier, but at this point in the game, you guys have done enough calculus that you recognize this as being a natural log integral. So when we go ahead and resolve this, that right side is going to come out to be the natural log of the absolute value of Q minus C times the EMF, capacitance times EMF. And you say, and this we're going to do from the bounds from 0 to Q. When I go ahead and resolve that, I'll put in a Q. So I have the natural log, absolute value Q minus C EMF, minus natural log, when I put in a 0 for Q, now, there's a cool property of logarithms that when you subtract logarithms, you can turn that into a division, right? And so we're going to use this weird property of logarithms. By the way, I think it's pretty wild that like logarithms have a purpose and that they actually get used for real things in real life. It's not just some weird mathematical construct that mathematicians came up with. It's kind of, in a way, pretty cool to be using this stuff that they taught you in math, and you're like, when is this ever going to apply, right? And your math teachers assure you, oh, natural logs, you'll need them at some point. Did they ever explain why or what sort of things that come in? It's just neat to see them actually being used. So this is what we're getting. So there we go. Hey, look, I've got an equation that has Q and T, right? So now my goal is just to get the Q by itself. So I can say Q equals, and I have an equation I can plug in anytime and solve for what the Q on the plate is, the charge on the plate. So you say, okay, all right. So I just need to go ahead and now do some math and rearrange this. You say that's no biggie. I just have to remember the way natural logs work, the way logarithms work. Remember that if I had something like a log base base B of A equals C. You know what that's really saying? That's really saying B to the C power equals A, right? Is what this really is saying, right? Yeah. So in this case, natural log, that's a log base E. So E to this power equals what's in the argument of the log here, right? So that's what we're going to say. So we're going to rearrange this mess, and we're going to say E to the negative T over RC, right? E to this power, that's going to be equal to this. Okay. Do you mind if I play a little fast and loose with the absolute value sign now? Okay, I'm just going to drop that off, not worry about it. Okay. You're just going to trust me that it's going to work out okay. All right. I can go back later and explain why this is for sure going to be a positive value. It's almost like cheating to show you that ahead of time. Should I show you now? Sure, why not? Do you remember that C times the EMF? Look what that is. That's the maximum charge we're going to get on our capacitor plates. So if I take the charge at any point in time minus the maximum, that's going to be a negative. And then look, that's the maximum. It's a negative. The two negatives are going to cancel. I'm going to get a positive value always for this. So I can just drop the absolute value signs and not worry about it. Everything's going to be great. Okay, so there we go. So what do I do now? Let's go ahead and I want to get the Q by itself. So first I'm going to multiply both sides by negative C EMF to get this out of the denominator. Look at that. Look at that. shaping up great. And now what I'm going to do, I'm going to add this CEMF over to the other side. Look at this. Look at this. You know, every time I do this calculation and it like works out, it makes me feel so good about myself that I was able to do this. And so now what I want to do is I can go ahead, I can factor out that CEMF just to make this look pretty, and because there's something really important I want to share with you about that. 1 minus e to the negative t over RC. Right? So I'm just cleaning this up here, but there's a really important reason why I'm doing this. There's something really, really significant about the way this equation is laid out. Okay. And that is, I kind of just, like I said, I was kind of cheating showing you that ahead of time. But here, look, this C EMF, that's the maximum charge, right, on that capacitor plate. And so the way this equation is set up, the CE, that's really like the Q max. So it's like, look, my charge at any point in time is equal to the maximum that I'm going to get of charge, right? The maximum charge times this expression, 1 minus e to the negative t over RC. But here's the thing. This chunk here, okay, this bit, right? Let's think about what this is actually going to be equal to, right? At t equals 0, and then as we head to t equals infinity, right? When time is 0, this is going to be 1 minus e to the negative 0 over RC, right? So it's going to be e to the 0. E to the 0 is equal to 1. 1 minus 1 is 0. So at time 0, this is going to have a value of 0. As time heads to infinity, what's this going to be? Well, as time heads to infinity, I'm going to have e to the minus infinity over RC, which is just going to be e to the minus infinity, which is equal to 0. And 1 minus 0 is 1. So this will head to a value of 1. So this part in parentheses here is going to go from 0 to 1. You know what that's like? That means this is going to be like a decimal number, right? Point something. That's going to tell you then the percentage of Q max that you're at. Do you see that? So my charge on the plates at any given time is equal to Q max times this percentage. So this part is just telling you, like I said, the percent of the max value you're going to get. All of our exponential equations we're going to come up with will be set up like this, where you have your variable and then the maximum value and then some expression with a exponential here with a e, the natural, that's going to tell you the percentage of that max value you're at. That's like the setup, and that's how to understand and think about the equations. Ones like this that have 1 minus e to the whatever, these are things that are going to start at 0 and head to 1. We'll get some expressions that don't have this constant 1 in front, and then I'll just have an e to a power, and that'll be something that starts at 1 and heads to 0. Okay, you'll see that when we do the discharging circuit. But there we go. So this is what we were trying to get, and this is the way to understand what it's telling us. But we'll usually be using these variables, right, that they're giving us in the problem. So we'll write it like this. But remember that this is just the max value for the charge. Okay, so that's that derived. Well, we can do a bunch more stuff with this. Okay, we have just successfully checked. And I say, hey, is this in agreement with what we came up with here? You say, sure is, right? If I take a look at this, you say, look, at time 0, we're getting 0. At time infinity, this is going to give us C epsilon, or C script E, the EMF, right? Which is exactly what we said it should do. This graph, you know, recognize this is an exponential curve. That's going to follow a pattern just like this. Okay, success, that's what we were trying to get. Can we go ahead now and find some of these other values? Going to be really fast to do. Okay, going to be really fast. How do I find current? I'd like to now find current as a function of time. And you say, oh, that's not going to be bad. I can do current as a function of time. You say, because isn't it true that current, isn't that just dq dt? And here's the equation for Q as a function of time. Okay, it will be easiest if I start with this version of the equation. Okay, so I'm going to take this, and I'm just going to take the derivative of it with respect to time. And so you say to find that current, it's dq dt, so it's going to be the d dt of right. And you say, now remember, C and the EMF, the capacitance, the EMF, the voltage of the battery, these are constants. In R, resistance, and C, capacitance are constants. The only variable here is T. So when I take the derivative of a constant, that's just 0. And then I take the derivative of this, you know how to take the derivative of e to the x, right? You know what I mean? It's just going to be e to the x, right? So when I go ahead and take the derivative of this, you say that constant in front is going to stick around. But now I take the derivative of e to the minus t over rc with respect to t. That's going to kick out e to the minus t over rc, but it's going to kick out the derivative of this exponent, right? It's like a chain rule sort of thing, right? So it's going to kick out a negative 1 over rc. So a negative 1 over rc, and the c's are going to cancel, times e to the negative t over rc. And so what I'm going to get out of this is I'm going to get that the current is EMF over R times e to the negative t over RC. But here's the thing. Do you recognize what EMF over R is? What's EMF over R? EMF over R, that's that maximum value that we're going to get, right? And this is we start off at the maximum current, it's EMF over R, and then it's going to head to 0 over time, right? Is that what this equation is going to give us? You say, yeah, look, do you see this chunk that we're multiplying our maximum value by, right? This is going to give you a value at t equals 0, heading to t equals infinity. When time is 0, put in a 0 for t, e to the 0, this is just 1. And as we head to infinity, as t goes to infinity, right, e to the negative infinite, that's 0. So this is going to be, this chunk here is going to give us a value that is going to be like the percentage of this maximum current that we're at. Starting at 100%, heading down to, or 1, times 1, heading down to 0%. Okay, and that is exactly what we should be getting for current as a function of time here. It should be decaying down like that. Okay, from EMF over R to 0. So perfect, that worked out great. Can we find the delta V for the capacitor as a function of time? And you say, yeah, we ought to be able to do that. Okay. You say delta V for the capacitor is a function of time. We're going to go ahead and start. You say, well, the equation we're going to use for that is we're going to say capacitance is Q per delta V, right? That's my formula, right? And I'm going to rearrange this, and I'll say, hey, that delta V for the capacitor is equal to Q over C, right? Okay, rearranged. We now have an equation for Q, don't we? Okay, we got this, right? I'm going to use this one again. Okay, before I rearranged, made it pretty. Okay, so if I substitute that in, all right, I'm going to get that my delta V for my capacitor, and for Q, I substitute in that expression from before. The equation for Q was capacitance times the EMF minus capacitance times the EMF times E to the negative T over RC. Okay. But now I'm doing what? I'm going to divide it by C. When I do that, we're going to get that the voltage over the capacitor, C's cancel. This one on the bottom cancels a C in every term up top. And so what I end up with is going to be EMF minus EMF E to the negative T over RC, right? Factor out that EMF. 1 minus e to the negative t over RC. right? And you recognize that this chunk is going to be what? As time going from time equals 0 to time equals infinite, this value is going to go from 1 minus e to the 0. Well, e to the 0 is 1. 1 minus 1, that gives you 0. And things are going to decay down to when time is infinite. E to the minus infinity is going to be 0. 1 minus 0 is 1. So this is going to give you a decimal that goes from 0 to 1. What's this EMF? Well, that's the maximum voltage on the capacitor, isn't it? Right? I made it negative because I was going around that way when I was reading the circuit, but we recognize that's our maximum voltage, our magnitude of maximum voltage. And you say, and so this is going to give me the percentage of my max voltage I'm at, going from 0% to the full EMF when the thing is fully charged, right? And that makes logical sense, and it agrees with what we did here. Again, I did it negative. I made it negative because I was thinking about, as I'm reading the circuit, thinking about that. But you're right. We can think about the magnitude as being positive like this. What's left to talk about? One more, and that's, can we do the delta V for the resistor? And you say, yep, that'll be easy. The way we're going to find delta V for the resistor is we're going to go ahead and say delta V is IR, right? That's how you do it. And you know what? We have an equation for I. We came up with it before, right? Up here. I say, this is my equation for the current. And so if I go ahead and I substitute that in, we're going to say delta V for my resistor is the current, substituting in that expression for current that we got. EMF over R is negative T to the RC, T over RC over RC. So we're going to say times E to the negative T over RC. That's my current. Now I'm going to multiply by the resistance. So I'm going to multiply that by R. When I multiply by R, that's going to cancel with that R in the bottom. And so I am going to get that the voltage over the resistor, I don't know why I'm off center here, sorry, that the voltage over the resistor from one side to the other is just EMF E to the negative T over RC, okay? And once again, we recognize that that EMF, that is the maximum value for the voltage over that, right? Again, I made it negative because I was reading the circuit this way, going the other way would be positive. But anyway, the EMF, and it's going to drop to a voltage of 0 when the current through the resistor goes to 0 at the end, right? When current stops flowing in the circuit because it's fully charged. You say, so this here, again, we recognize that as we go from T is 0 to T is infinity, that our value for this expression, put in a 0 for T, E to the 0 is 1. And then put in infinite for infinity for T, you say E to the negative infinity is 0. And so this is going to give us a percentage of that maximum that we're at, going from 1 to 0 over time. And that is exactly what should be happening. We should be exponentially decaying, heading to 0 as time progresses. And that is these derived, the calculus done. And like I said, once you get that Q equation, the rest of these kind of follow bang, 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 knowing that we're using our equations for capacitance and our equation in Ohm's law to solve these. Are there more things we could figure out as functions of time? Yeah, we could figure out other stuff about this circuit than what I put in this chart. We could do power ratings, couldn't we? We could talk about how quickly energy is being converted to heat in the resistor, or how quickly power is draining from the battery or whatever. We can do power calculations, and we have our choice of various ways of doing that, right? Since we know that, and I don't know, I'm going to scribble this. I don't know. And I say, well, I know, for example, I know that power in a resistor, how quick, now specifically for a resistor, right? You could say power is I squared R, and we have an equation for current current as a function of time in the resistor, right? Okay, the current that's flowing in the circuit here. So I could easily just take this, square it, and multiply by R, right? And that would go ahead, that would give me my power, how quickly energy is being burned off in the resistor, right? I could go ahead and I could figure out, and that'll be also talking about how quickly we're taking power out of the battery too. We could do, power is I times delta V, right? And I could think about the battery and how quickly we're delivering energy to the circuit from the battery, and that would be I times delta V, right? And so that would be the current in the circuit, which again, we have this expression for, and I multiply by the voltage of the battery, and that's how quickly the battery is pumping out energy. Some of that energy is going towards potential energy in the capacitor, and some of it is being burned up, converted to thermal energy. It's getting destroyed. Converted to thermal energy in the resistor. So the power rating of the resistor is not going to be equal to the power rating of the battery, because some of the energy goes to potential energy here, right? And we can talk about energy being stored up in the capacitor, and from here we can go to like finding the potential energy as a function of time, and because potential energy, the energy in a capacitor, right? You remember that's equal to 1/2 C times the voltage over the capacitor squared, right? Okay, and since the voltage is changed as a function of time that we calculated here, we could slap that in there. We could find the energy in the capacitor as a function of time. There's like all kinds of cool stuff we can do, but this is enough for today for this. And so this is the calculus behind charging a capacitor. Hope this followed along. It made a lot of sense, and we could figure out all kinds of other stuff to it, and that all this makes sense at this point. What's left to do, we could talk about discharging a capacitor and run through that, and maybe do a little bit more complicated circuit than just the simple one, and take a look at how that would work. All right. See you in the next video.